Imagine stepping into an elevator on the equator and quietly riding all the way into orbit. No thunder of rockets, no plumes of fire, just a smooth climb into space, held up by an invisible thread reaching beyond the sky. For more than a century, scientists and dreamers have imagined this ultimate ladder to space, a structure so tall it touches the edge of orbital mechanics and maybe the limits of what humanity can build. Is a space elevator real engineering waiting for its moment? Or is it still science fiction wearing a lab coat? That is the question we will unpack in this documentary. To answer it, we have to move beyond rockets and think in terms of gravity, rotation, and materials so strong they almost sound impossible. Picture a cable anchored at the equator, stretching far into space, with a counterweight at the far end. As Earth spins, the whole structure is pulled tight like a string on a spinning stone. Elevator-like climbers would crawl up and down this tether, powered by electricity, not rocket fuel, turning access to orbit from explosive launches into something closer to a long-haul train ride. Instead of burning thousands of tons of propellant for every launch, the energy could come from ground-based power stations, solar farms, or beamed energy systems, dramatically cutting the cost per kilogram to orbit. For launch providers like SpaceX and Blue Origin, that live and die by cost per kilogram, the idea of shipping cargo to orbit for a fraction of today's prices is nothing short of revolutionary. The environmental impact could also be profound. Fewer launches mean fewer emissions, less upper atmosphere pollution, and a quieter sky over coastal spaceports. But this bold idea started long before Falcon 9 or New Glenn, long before the modern launch industry even existed. In 1895, Russian scientist Konstantin Tsiolkovsky looked at the Eiffel Tower and imagined a tower so tall it reached geostationary orbit, a thought experiment that planted the seed for the space elevator concept. Later authors like Arthur C. Clarke would turn it into iconic science fiction, while modern engineers translated that fiction into equations and stress models, trying to see if the numbers add up. To understand whether a space elevator can exist, we have to understand the invisible battlefield between gravity and centrifugal force in Earth orbit. Geostationary orbit sits about 36,000 kilometers above the equator, where satellites circle the planet once every 24 hours, matching Earth's rotation and hovering over the same point on the ground. If you hang a cable down from that orbit toward Earth, the lower parts feel more gravity than outward pull. They want to fall down, while the upper parts feel more centrifugal force and want to fly outward. Stretch the cable far enough beyond geostationary orbit, add a heavy counterweight, and the outward pull balances the downward pull. The whole system goes into tension and stands upright, locked to the spinning Earth below. This tension is what makes a space elevator possible, but it also makes the engineering brutally unforgiving. Every centimeter of that tether is under extraordinary stress. Move a climber up the cable, and you shift mass higher into orbit. The tension changes, the system flexes, so the dynamics have to be carefully modeled to avoid dangerous oscillations and resonances. Engineers talk about the space elevator as a kind of inverted skyscraper balanced not on foundations of steel and concrete, but on the precise dance of orbital mechanics. So if the physics check out, the next brutal question is this: what do you make a 100,000-kilometer-long cable out of? No existing bulk material, steel, Kevlar, even advanced composites is strong and light enough. A space elevator demands a tether whose tensile strength-to-weight ratio is far beyond conventional structures. In the early 2000s, carbon nanotubes looked like the miracle answer, tiny cylindrical molecules of carbon with theoretical strengths many times higher than steel at a fraction of the weight. On paper, a ribbon spun from perfect nanotubes could handle the stress, but in practice we still cannot manufacture flawless kilometer-scale fibers, let alone something stretching a tenth of the way to the moon. Researchers now explore alternatives like graphene-based materials, hybrid composites and tapering designs where the ribbon gets thicker higher up to spread out the stress more efficiently. Even with a perfect material, the tether would constantly face micrometeoroids, atomic oxygen, and space debris. Every grain of dust at orbital speeds carries the energy of a bullet. Designs call for multi-layered ribbons built from many smaller strands interlaced so that damage to one strand does not sever the entire cable, allowing robotic systems to patch and weave repairs in real time. Just building the elevator would be its own epic campaign. One approach launches a spool of tether from orbit, slowly unreeling it downward to Earth, while simultaneously extending another section outward to keep balance. As the tether grows, it passes through layers of atmosphere, through jet streams and storms, until it finally reaches a waiting ocean platform somewhere along the equator. From there, engineers would gradually increase the thickness, adding more material ships and rockets, feeding the construction until a full-strength ribbon stands between planet and orbit. But long before the ribbon meets the clouds, it has to survive Earth's messy and unpredictable environment. Hurricanes, typhoons, and intense wind shears hammer equatorial oceans, and any structure passing through this chaotic air would experience constant vibrations and bending loads. Lightning protection becomes critical. A conductive ribbon could turn into a giant target for electrical storms requiring advanced grounding systems, plasma shields, or active charge management. Space debris higher up is just as dangerous today. Low Earth orbit is crowded with defunct satellites, boosters, and fragments all moving at several kilometers per second. A collision with a large object could sever the ribbon, triggering a catastrophic whip-like recoil that might wrap debris around the planet and devastate anything in its path on the ground or in orbit. Defending against this might require an active traffic control system for orbit, nudging satellites and junk out of the tether's path, and possibly using laser or tug vehicles to clean up the most dangerous debris. Then there is security. A space elevator would be critical infrastructure, a single vulnerable line connecting planetary industry to orbit, making it a prime target in conflicts or terrorism scenarios. Some proposals relocate the base to floating platforms far offshore, with international treaties treating the elevator more like a shared ocean route than a single nation's asset. And that raises one more towering obstacle: politics. Who owns the elevator? Who sets the prices? Who gets priority access for cargo and crew? Building it would demand investment on the scale of the largest infrastructure projects in human history, likely requiring a coalition of governments, private launch companies, and orbital industries, not unlike today's sprawling space economy. So when could any of this actually happen? Are we talking decades or centuries? Right now, most space elevator work is theoretical and experimental, focused on materials research, tether dynamics, and small-scale prototypes rather than full-scale construction plans. Competitions have tested climber vehicles powered by lasers and cables dangling from helicopters, proving that energy beaming and traction systems can work on a small scale, even if the ribbon to space does not yet exist. Most realistic roadmaps put a full Earth space elevator beyond the mid-21st century, waiting for breakthroughs in mass-produced ultralight materials and global cooperation that simply are not there today. But variants may appear sooner. One idea is to build a shorter elevator on the Moon or Mars, where gravity is weaker and there is no thick atmosphere or crowded debris field to contend with. For companies like SpaceX and Blue Origin pushing heavy industry into orbit or onto the Moon, early off-world elevators could become freight spines feeding propellant depots and construction yards in cislunar space. Farther in the future, imagine not just one Earth elevator, but a network orbital highways linking equatorial bases with lunar tethers, Mars elevators, and rotating habitats, forming a kind of interplanetary logistics web. If that happens, the way we think about going to space would change forever. Rockets might handle fast trips and deep space missions, while elevators quietly handle the bulk cargo, the way shipping containers do today. Tourists could ride to orbit without enduring high G-forces. Researchers could shuttle between orbital labs and Earth as routinely as flying overseas, and heavy industries might move off-planet entirely to keep Earth cleaner and quieter. Standing at the base of such a structure, looking up at a ribbon vanishing into the blue, you would be staring at a piece of infrastructure that redefines what it means to be a planetary civilization. So is the space elevator science or fiction. Today, it is engineering constrained by materials politics and risk a vision that fits within the laws of physics, but not yet within the stockrooms of our factories. Rockets like Falcon 9 Starship and New Glenn will likely dominate access to orbit for decades. Their reusability and falling costs continually pushing the elevator further into the future. but also building the orbital economy that might one day need it. If breakthroughs in materials arrive, if international cooperation can match the scale of the idea, and if we decide that the payoff is worth the risk, the first space elevator could turn from thought experiment into construction project. Until then, the space elevator stands as a kind of mirror for our ambitions, asking, not just can we build this, but what kind of future we want for our species among the planets. Would you ride that first elevator to orbit? Would you trust a ribbon of exotic fibers and international treaties to carry you beyond the atmosphere, or would you rather strap into a rocket and light the fuse? If you want to keep exploring these questions and follow how companies like SpaceX and Blue Origin might pave the way for whatever comes next, make sure you subscribe to Beyond Delta Vive. Turn on notifications so you do not miss our deep dives into the future of spaceflight, from reusable rockets to orbit-spanning megastructures and beyond.